All right, now your book has, at this point, there's a pause and there's a little review. So I just want to do what they do just because, despite my trashing the book, they get, I just wrote in this pen 1 second ago. Okay, well, I'm going to skip out on the rest of my day. Last backup. Last one. Okay, so the problem is if I leave the cap half on, it destroys it. Okay, so review, what am I reading? All observables are related to an operator. Now, I've said that a million times. Maybe you don't even need to write that down, right? There's nothing you could ever think that you could ever measure that somebody hasn't figured out a quantum mechanical operator for. But you know, actually, I have to go back on that. When I've seen some really technical problems, let me give you one. An electron is moving through a semiconductor and it gets near a dopant and it changes direction. That's called scattering, right? It gets near a dopant and it changes direction. Apparently, no one's really sure what the operator is for that. Anyway, but you get my point. If I'm going to describe something that's real, there's an operator for it. And maybe there's one or two that people aren't sure what the operators are, but anyway. So that's just, I thought that was kind of a neat example. I was just reading about that the other day. And kets, of course, are, how do they put it? State vectors. And by state, of course, it's what state are you in. I've seen more complex definitions of state as a system that can be characterized with a very few numbers of descriptions like pressure, volume, anyway. So I've seen more technical descriptions of that, whatever, I think you know what that is. Of course, the observables are eigenvalues. So eigenvalues, right, so you have an operator, you have a state, the operator on that state, the eigenvalues, of course, the observable. Again, we covered that a whole bunch of times. But this one is nuanced, but it's definitely true, which is operators have what is change states. Now, this isn't like really something you need to worry about or memorize, but it does happen. So, example, I measured the absorption of a molecule, right? So there's a measurement. I just said measurement, so there's an operator. The operator will probably be the transition dipole operator because I have a ground state and I shine light on it and it goes to an excited state. That only happens if there's a change in dipole moment, if I'm using light. Okay, so I have a dipole operator, I've got a ground state, but and of course the eigenvalue of that transition will tell me what I observe in the spectrum. But notice that the ground state becomes the excited state in the process, right? You land in the excited state. And you have to worry sometimes that excited state is reactive with oxygen. So if you're measuring the optical spectrum of the chromophore, it'll occasionally go into a triplet excited state and react with oxygen and be destroyed. So that's, and again, you learned that as freshmen, but we'll just try to make that make that as solid as possible. Another example, is that all I wanted to say? Yeah, that's all the book says. Well, here, let me give an example. So you have a state, which I was kind of representing last time with a generic little gamma. And it goes into, let's say, an eigenstate of a Hamiltonian. It doesn't have to. The idea that would happen would depend on how much of this state is present, how much of this eigenstate is present in the chemical state to begin with, which hopefully you've seen enough of this to know now that would be this. So this is like the percent composition of this eigenstate into the prepared state, the thing that you're interrogating. And you know, we've seen this, I've written this several times now. That's what I call a generic coefficient of how much of this state is represented by a complete basis set of states of a particular operator. Okay. So again, maybe this isn't super clear, so let me again just remind you, and then I'll even degenerate to the point of rewriting this as in the form of spin, you know, Stern-Gerlach this and that, because that hopefully is easy. And again, this is just what I just wrote is a manifestation. I didn't write the coefficient the same way. Let me fix that. That bothers me. There we go. Okay. So still just reviewing. Okay, and so again, the absolute value square of that represents how much of whatever particular state, maybe that's the ground state of the operator, is in the state that is being studied. And again, if this is a little too abstract, let me point out that, let's say you're studying silver ions, and they're in some state. Now, they may or may not be in the state of interrogation. Now, let's give you an idea of what is being interrogated by, of course, we need an operator. The Stern-Gerlach device is an operator, and it will be in the Z direction. Okay, so here's my state. Here's my operator. Now, you know that I haven't said what these things are. They could be out of a furnace, in which case I have no idea. Or maybe there's a Stern-Gerlach device behind it. I haven't said. Okay, now anyway, the SZ1 will produce plus and minus Z polarized. But I put a block, so this is going to report on the SZ plus. How much is an SZ plus? And of course, it's going to end in that state. All right, so beams coming in, however they came about. I'm assuming, let's just say they're out of the furnace. That means it'd be 50% up, 50% down with respect to Z. Okay, out comes the ions. I block one of them. I can measure the intensity on top, and I can see that's half of the input. Okay, so now I made a measurement. And of course, they're leaving in the SZ plus state. So whenever they came in, that's up and down polarized. They're now being up polarized. So I've changed it. It's not the same state anymore. It's related, but not the same. Now, also on your homework, hopefully, and again, I'm getting you an answer here. This is what the operator is that represents this measuring device. This is the projection operator. This queries how much is up polarized, and this says, and you're going to leave in that state too. So now you can see a little bit more about why operators always come in this ket-bra combination, because your bra is always like projecting, which is why they're kind of complicated. And okay, the ket part is always going to be easier enough. That's just your leading state. Okay, so again, I'm still just reviewing, but now let me point out something kind of neat, which is hopefully in quantum 1, as an undergrad, you may recall, seeing expectation values. We covered them at the first week of class. They're in my silly textbook, and of course, I mentioned the first example I had of this was how do you measure the momentum of a sine wave when sine is not an eigenfunction of momentum? And I said you do an expectation value. Okay, you may be wondering why the heck am I going back to this? You may notice that symbology? That's where we got it from, Dirac notation. Watch this. Let's now do this. Let's do bra, ket. Okay. Help if I did it right. Okay, when I see that, I usually am stuck because I don't necessarily know what my state is or how to deal with it. So I'll do two resolutions of the identity because I always know what those are. And let me switch order of my dashes here. I think I got this from the book. I don't want to stray too far from the book. Okay, so and I'm going to start in between. So you actually have some leeway sometimes where you put these resolutions of the identity. Here I really don't. It's going to have to be between the operator and the state. There's literally nowhere else to go. Okay, there's the number one. And then on the other side, there we go. Okay. Now, as usual, I'm assuming that in this particular notation, I hopefully have been pretty consistent, that I'm assuming that these A dashes are eigenstates of the operator. Yeah, I can say I think I can pat myself on the back for being fairly consistent about that. So when I put that here, what I'm going to get is I'm going to A double dash. I'll act on the right, and then a Kronecker delta, which again, if you just stop there, 5 points off. What does it do? Its job is to kill sums, It's 0 unless A double dash and A dash are the same. All right, now you have a choice, and whatever you choose, just stick with it. I can kill off either one. It doesn't matter really which one you do. I'm sure there's some convention that maybe kill the one to the right or kill the one, I don't even know. It really doesn't matter. But hopefully it will be consistent with the book. And the book killed off the double. The book killed off that much. Again, it doesn't matter, but I'll do that. Okay, so again, every time you see an A double dash, you write A dash. That's what it does. Kill the sum. Every double dash becomes dash. Right, so now what do I got? Okay, I got an A. I got an eigenvalue. Let's see here. Okay, what I'm going to do is this guy, there's nothing I can do with it. So but what I'm going to do, for reasons I mentioned last time, I'm going to flip it over because projecting a state into a ket, into an eigenstate is usually easy. So let's go back here. Let's say that I get 50% on top, and of course I killed off the 50% on bottom. All right, let's say that that's what I did. Well, this state is 1 over square root of 2 plus 1 over square root of 2 minus. So I know that. Okay, that information I just gave is this. If I flipped it over, I can still answer the question. It's just now I'm kind of confused because what I just described, looking at this and figuring out what this is what this is. This is projecting the state into the basis. That makes inherent sense to me. But to do the opposite, to say how much of the plus state is in here, again, I can do it. It's just a little bit weird. It's like working backward. Of course you can do it, especially if you already know the answer. But don't. Okay, so there's that. Now this, actually, I have a double dash here, but it doesn't matter. You know what it doesn't matter? Because I can make the double dash single dash. And that's why that's a single dash, by the way. I could technically do that. Anyway, here, let me just wipe it out. Anyway, if you're wondering how that happened, that's how that happened. Again, single dashes, double dashes become single dashes. State. Okay, now you may notice that this is the sum of the coefficient squared times the eigenvalue. Where, again, I'm counting on at this point, you're sophisticated enough to know that this is the absolute value. There you go. Yeah? Okay with that? And again, this is how you represent the state. Here, here. That's how they're related. And again, when you're working with beams of silver ion, actually they're not ions, they're technically neutral. Anyway, when you're working with beams of silver atoms and your homework, and I tell you, oh, it's SZ plus, oh, it's SX plus, I'm going to throw that at you. Make it SZ plus. Make it as silver atoms that are SX plus. Do that. Run it through this operator, which of course is going to have some, run it through Stirner-Gerlach, which will have a corresponding operator. Like I say, you'll figure it all out. Last bit, all right, has anyone seen this before? Is this, a lot of you are saying you never, this doesn't, no? Okay, how do you interpret this coefficient? Remember, I actually said something about it a minute ago. Coefficient squared, absolute value. By itself, it's meaningless. When it's the absolute value squared, like a wave function squared, what is that? Probability. It's a probability. Okay. Here is a measured value and times the probability of that value. So, if you were to take dice, 6 dice, and there are 6 sides, and roll it, and sum them, you don't really know what you're going to get, but what's the most likely result? Yeah? Yeah, it'd be like, yeah, right? On average, you would roll, well, I guess a 3, or I guess a 3.5. So okay, that was kind of a bad one, right? I guess you would on average roll 3.5. And times 6. So, what's 3.5 times 6? 28.
21. Oh, that's 7.
Now I'm going crazy. What's 21? Yeah, you were right. Sorry. Right. So, nothing says on a particular roll you know what you're going to get. But on average, if the average value of the dice is 3.5, right, from 1 to 6, and yeah, there you go. It's the same thing. Especially if you're thinking about measuring a large number of things at once. Again, it just makes more sense that the probability of the particular single measurement gets amalgamated with all the others as represented by their population, which is the same thing as their probability. Those are the same number. Yeah? We're all okay with this? Yeah, not too bad. I just want to point out that you had seen that before. Okay. Now to get into the material for those last few questions. And this is something I see constantly. Now, chemists, we're only doing electrons. If we were in physics, we'd be thinking about quarks and the occasional lepton. Oh, sorry, God, electrons are leptons. Anyway, those guys worry about all kinds of stupid stuff. We're only worried about electrons. So the fact that an electron is spin 1/2, where spin is that thing we don't really know what it is overwhelming. It's half of what we need to do, it's half what we need to worry about. And it also dictates, remember how a little bit of that last homework, and I mentioned in class, how you have to write wave functions of electrons in that anti-symmetric way. So again, I don't spend a lot of time on atomic structure. I'll have some more on the homework because you should know this stuff. But wave functions for electrons have to be written in that anti-symmetric way, anti-symmetric for interchange, because they're spin 1/2. And that keeps them from occupying the same state simultaneously. So that's a really big deal. Okay, so the next thing we're going to cover are matrix representations. I know to some degree we've already covered a lot of this, but not really. All right, so we're going to get into a bit more detail. Specifically, take that last example. Okay, my operator was basically the SZ operator. So you actually haven't really seen this yet. Kind of. The eigenvalues, I've been saying in words, are plus or minus, now technically h bar over 2. So remember, the type of spin that we don't know what it really is spin is spin 1/2, and so in quantum world, for some reason, angular momentum always seems to want to show up as h bar. The spin, some fractional value times h bar, 1/2, 0. Higgs bosons have 0 spin. Electrons are 1/2. Protons, neutrons are 1. Like a pi meson is 3/2. Anyway, so you see these come in these half integer forms, including 1 and 2, 3. Okay. All right, so if I operate on the SZ plus state, of course I get h bar over 2. Again, it kind of looks like I've been talking about this already. Kind of, you'll get a little bit of a different flavor. Okay, and so that we're not just, so maybe I'm not just wiped out, and I did this a little bit on the homework. The SZ is the basis set. SZ plus SZ minus, that's our basis set. So let's just call them plus and minus. SX and SY, I'll call those X and Y, I have to. But I'm going to reserve a special notation for SZ, and I should do that. I should always do that. Basis sets, these span Hilbert space, right? There's only up and down, so that's Hilbert space. These represent up and down, and I can cast everything else in the form of this. So that's absolutely what a basis set does. That's what it is. Okay, and this one's important. This one is horribly, horribly important. Now you've actually seen this before, but I'm gonna restate this in a way that's like way more important because it answers a lot of your upcoming questions, if anything. An operator in its basis set, representing it in the states that are its that are its eigenfunctions, its basis set is diagonal. Okay, now that was a whole mess of words. Let me write this down, and you'll hopefully remember that because I brought it up over the last 2 lectures. Right? So I can see now, for one, hopefully we're all kind of immersed into matrix mechanics of quantum mechanics. We've done nothing. Matrix. Right here. The fact that that was a delta function, oh, I deleted it. The fact that it was a delta function means that it's diagonal. Now, if you don't see that, ground state, first excited state, second excited state, second excited state. Right? There's no ground state, first excited state. There's no ground state, second excited state. I don't see that. That means that this is a diagonal matrix. Okay. Now, again, I've actually covered this before. Hopefully, even if you don't remember, hopefully what I just said makes sense. And again, you can see that right here. Hopefully this makes sense. But let me point out what is useful to you right now is that this can allow you to define operators that you don't already know what they are. Again, you need it on your homework. All right, so in the case of SZ, so let me say, so therefore SZ, so what do you do with this? Let's say, now tell me what an SZ operator is. Okay, well, it happens to have every eigenvalue of h bar over 2 sorry, let me, eigenvalue basis, eigenvalue basis. Right? So now what I can do is I can just factor that. Let me just factor that, it's a heck of a lot easier. There we go. Okay, so notice that I was able to define the SZ operator. Sum of the diagonal elements of the basis. Yeah, we're using some fancy words, right? Times their eigenvalue. That's just why you put a minus sign there. Okay. When we get to SX and SY, you're going to hate life. It's going to take a while. It doesn't sound like, well, it wouldn't be any different. It's a lot different. And I think you have to do that on your homework. Okay, now again, to reiterate the matrix form, this is also a matrix. That would look like this. Here's the diagonal. Here's the other diagonal. Okay? Now I got to remind myself, it's the bra that's on the left. I'm trying to figure out which one becomes minus. Is it this one or this one? It's this one because I went downward. And then just do the opposite for the other side. Okay, that's the matrix representation. And you should see that this will spit out h bar over 2. And that leaves a plus plus, right, inner product. A plus ket projected into a plus bra. How much percent plus is plus? Well, it's 1. Okay, here I've got a minus h bar over 2. And then I have to ask, how much is the minus state? How much is in the plus state? It isn't. Vice versa. There you go. So now you've got the SZ plus SC operator. Okay, next thing you could do is act on it with the SZ plus state, which of course is 1, 0, and you end up with h bar over 2, 1, 0. So, therefore, okay, so there you go. Operator states, all this makes sense. Operator eigenstate, eigenvalue, same state. So on your homework, I'm going to have you do this. Well, actually, I start you out with this because this is easier. And then in the latter questions, then I make you do it this way. Let's do it that way. Okay. I did it this way. I just did it this way. I'll do it this way. They're the same thing. They're not different questions. Okay. H bar over 2 plus, plus, plus. See, I just brought this in here. Remember, rules of algebra apply. Minus h bar over 2, minus, plus, sorry, but that's 0. Minus plus is 0. So there you go. Plus is 1. H bar over 2 plus. H bar over 2 plus. Same thing. So I have you go back and forth. Between matrices because again, it just really forces it into your head. You don't have the choice. You totally get it. I've done this a zillion times. Okay, now the problem that we run into is there's literally nothing more to do with Z. I've taken I can apply it to S minus, but whatever. Right, that's stupid. You get H bar minus. H bar over 2 minus. That's literally all I can do with this. You've seen every piece of quantum mechanics I can do with SZ. Which means now I'm going to do SX. SX. And SY. Now, what are they? I need to figure out what the states are. And by the way, you've seen them before. I showed them to you before. I just gave them to you, and you said, okay, that's what they are. This time we're going to prove what they are. All right, now once I have these, you see, then I can get the SX operator. This same trick. It's eigenvalue in the state, and of course there'll be a SX and a minus SX. And we'll do the same thing for SY. So this is why, so hopefully this wasn't mind-blowing, but now you can see how much further we can go with this, and we can actually go pretty far with this. We're going to take several lectures, by the way. Okay, and we're also going to do this in the SC basis. If we solved SX in the SX basis, it's identical to this. I just replace all the Z's with X's. Cool, but it leaves me nothing to do. Now, another reason that we need to do this, you're thinking like, well, then that's the answer. No. What if I'm doing a Stern-Gerlach with an SX polarized with a magnet pointed up and down in Z? See that? You can't just wipe out the Z's and replace them with X. You can't just do that because sometimes your polarization or your magnetic field are 90 degrees. In which case you have to do it with let's pick an SC basis set. You have to pick a basis set. Okay, so how does this go? How is this going to go? Well, you're going to love this. All right. So we're going to define the state, and then we get the operators. That is the order of operations. So let's take an SX plus. Let's run it through a Stern-Gerlach in Z. And it turns out, now we won't have a beam block, we don't need to. Of course, the magnetic deflection is upward, and we could beam block the downward and vice versa. And what you see is a 50-50 split. So you see that half of the input goes up and half the input goes down. Okay, now what I'm trying to do here is I'm trying to build SX plus and minus in the SZ basis. That's what I'm trying to do. This is instrumental to knowing that, because now what I can do is say, and we'll do SY in a minute, and I'll do the plus state, is 1 over, not 1/2, 1 square root of 2. Remember that this 50-50 split, half up, half down, that's the absolute value of the weight of the plus minus. That's the absolute value, which is the square of the coefficient. So therefore I take the square root in the plus Z. There you go. And again, I'm hoping this is intuitive and ask me if it's not. Okay, now I'm going to do something, and again, I'm copying your book here. You're not going to like this too much. I'm going to have what's called a phase factor. Okay, so let me write SX minus. Now it's also going to be here, I'll explain this in a minute. Let me just write it down. There we go. Okay. So what we're doing here is, what I've really done here is, I probably went a little too fast here. Okay, what I've done is I have a phase factor. I can represent SX as SZ plus and minus times some phase factor. Yeah, what the hell does that mean, right? Okay, now phase factors are relative, so what I can do is I can make this, I can adjust this to be 1 and then figure out what that one is with respect to that, which is what I've done here. But okay, still that doesn't help explain it. So here's what's going on. Let's say let's look at SZ plus and SC minus as X and Y. Right now, those are orthogonal directions. Right? They exist in the same world, say polar space, but the dot product is 0. Ultimately, they're not the same thing. And they're not, one does not have any characteristic of the other. They live in the same world, but they're ultimately completely opposite. Okay, that's all fine. Now what I'm doing here is I am going to represent Sx. I'll start with plus. Sx is going to be on this plane. It bothers me. The arrow needs to be straight. The arrow's not straight, the world will end. Oh, there we go. That's the stuff. All right. Sx is on this plane. Now, S minus, Sx minus needs to also be orthogonal to Sx plus. Now, Sz plus and Sc minus are orthogonal by being 90 degrees apart. Their dot product is 0. Sx plus and Sx minus must also be 90 degrees apart. They have to be 90 degrees apart, right? But now who says where, right? You see, this is the phase factor. That's the phase factor. I never said where in the plane they have to be. They just have to be 90 degrees apart. That's the only stipulation. Now, what I can do is, and I've actually already done this, I can actually lock one of these to be square root of 2. See what I've done here? I've basically locked Sx plus, Sz plus is represented by 1 over the square root of 2. So basically, I forced them to overlap this much, but I still need to define their relative phase since they're 90 degrees. So, sorry, so anyway, okay, so big picture, Z plus Z minus orthogonal, like X and Y, Sx plus Sx minus must also be orthogonal, but what I'm trying to figure out is where they fit on here. Now, what I've done is, by saying that I'm going to make this phase 1 and then figure out that one, is basically I'm actually following the drawing I just made. I pointed Sx plus so that its projection into S plus, Sz plus is 1 over the square root of 2. I've defined this vector. Now what I'm doing is I'm going to look for this vector. To do so, it's got to be orthogonal, and it's got to also be consistent with Sy. We'll see that in a minute. See, Sy has got to do the same damn thing. They've all got to be orthogonal to each other. Sx has to be orthogonal to Sz, has to be orthogonal to Sy. Sx plus Sx minus has to be 90 degrees. Sy plus Sy minus has to be 90 degrees. And plus and minus are automatically 90 degrees by definition. So I've got to make all of these work together. Now, real quick, let me show you. Okay, now let me turn it 90 degrees. Here's plus, here's minus, right? Now notice that what I've done, now I'm going to figure out where X is, right? Now my arm's got to be 90 degrees, but I've got to figure out where it goes. So what I've done is I've actually gone this way. Okay, and of course I'm going to figure out that this is actually 1, and these are going to end up being 1, 2. You'll see that in a minute. Okay, now the problem is, where's Y? Where's Y? Because it's got to be, that Y plus and Y minus are still going to be 90 degrees, right? But where in this plane can they fit? And still be orthogonal. How can I put Y and still make them orthogonal to everything else? It's a nasty trick, by the way. The answer is? It's this! Lifting them up. You're going to lift them up out of the plane. How do I do that? You've seen it before. Here's the real plane, right? These are real numbers. So what plane am I pointing up? imaginary, you point it up into the imaginary plane. Real plane, imaginary plane. So that's how you're going to do S1. Okay, anyway, big picture, that's what's going on. I know this is, the book doesn't really explain this, it just says, oh, it's a phase factor and a relative. And that's very unsatisfying, because that doesn't, that actually really does, I can tell you honestly, that doesn't mean anything. Well, it does. This is what it means. They don't explain it. So that kind of sucks. I hopefully you've got it. I hope you've got it. Okay, so now with this, now we got the operator. And this is going to take a while. As I mentioned to you, this actually does get quite a bit more complicated than you would like to see. Okay, so there's this. Now again, we know from Stern-Gerlach that if we simply had the magnetic field turn 90 degrees, you still get up and down, just in the x-plane instead of the z-plane. So that's why I still got h bar up and h bar down. Up, down is relative, right? Okay. Oh, that wasn't so bad. Yeah, but now I need to put this into every one of these. See that? Yeah, this sucks. I told you this would suck. Write in very, very small letters, by the way. Okay, there we go. See what I mean? Okay, that's a ket. I've drawn that as a ket. Now, the bra, a number can fit in between a ket and a bra. Numbers can go anywhere. I'm not violating any rules here. But now that was a ket, now I have to do the bra. Notice how I made the phase factor minus. Remember, when you go from ket to bra, any number turns into a complex conjugate. That was one of our rules for kets and bras. Okay, that was this one. Now let's do the next one. Yeah. I was actually looking at my different parentheses versus brackets. Okay, there's my x. 1 over the square root of 2. And here's my bra at this point. All right. It's not that bad. It's kind of bad. Okay. Now, square root of 2's multiply through. So I got h bar over 4. 2 e to the. So you just got to kind of do this. And then, of course, let me just do the factor of 2. What I like here is I got an h bar over 2. I know that first minus, that minus delta 1, I know you want that to be a plus. It just feels right if it was a plus, and the second one was actually a minus, but it isn't. You have to just FOIL this out. Now you may also notice that when I write that as a matrix, it's going to be off diagonal. You see that? You see how, remember SZ had plus plus and minus minus? This guy's got plus minus and minus plus. This is going to be an off diagonal matrix. It also means that SX plus and SZ plus and SZ minus are not the basis state of SX. if SZ plus and minus were the basis of SX, then SX's operator would be diagonal, and it isn't. It's off diagonal. It's purely off diagonal. Okay, with this, let me in here. That's Y. So, sorry to rush here, but I'm trying not to. This says a different phase factor, by the way. A different phase factor, because it's not the same. And then therefore the operator is this. Okay. Now, let me tell you where I'm trying to get with all this. What I'm trying to do is figure out what these phase factors are. Once I have them, then I know for certain what the states and operators are. So again, I've got this defined, but when it comes to X, I'm still trying to figure out how I'm rotated. And I also, at the same time, I have to be okay with this guy too. So I'm trying to figure them all out so that they're all orthogonal and consistent with Stern-Gerlach experiments. The way we're going to do that is we're going to have atoms go into an S, this is next time, a Stern-Gerlach in X. That's going to be what we're going to do. All right, then let's block the minus, we're going to let Sx plus go into another Stern-Gerlach in Y. And that guy, we're going to see, by the way, what you see is a 50-50 split. I think we were talking about this before. Okay, so again, I've got these states, these undefinable phase factors, but again, hopefully you kind of understand what I'm trying to do with that. I've done that for Y, I've done it for X here, and here's the operator. So I've got states operator for X and Y. What I'm going to do is I'm going to run a beam through two Stern-Gerlachs, one in X and one in Y. Now I know the output's 50-50. That information allows me to figure out, what I'm going to figure out is the relative phase factor, delta 1 minus delta 2. That information, there's only one value that allows this to be realized. Only one value of this equals pi half, whatever. That's the answer, pi half. Only that value will allow this to work. That's the idea, that's what we'll do next time. I know this is ultra painful, that's why I videotape.